Welcome to Technical Founders. My name is Carlos Lara, AI Technical Founder, and today we will learn how to perform neural style transfer with PyTorch. Now, this allows you to take an image and reproduce it with a new artistic style. So for example, suppose you have an image and then you want to apply a Picasso style or a Van Gogh style to that image and get that as an output. So it's very, very cool. So essentially the algorithm works like this. It takes three images. So an input image, a content image, and a style image, and it changes that input image to resemble the content of the content image and the artistic style of the style image. So it's very simple. The principle here, how it works, we have two distances. One is for the content and one is for the style. And for our input image, we want to calculate the distance between the content of the input image and our content image, and the distance or the difference between the style of our input image and the style of the style image. And that difference there is what we're going to try to minimize. That's our goal, that's our loss, and that's how our loss functions are going to work. So we have the distance between the style and the content for our images, and then we're going to minimize that. And then you'll see how it works. It's very, very nice. So here, first we're going to import some packages and select our device. So just typical, just torch, NN, and so on. And by the way, at any point here, feel free to pause and think about what's going on. So we import our packages, and now if we have a GPU, then we want that to be our device. We set it here as a global variable. And otherwise, we will just use a CPU. And for this case, CPU is okay. It's okay, but obviously a GPU would be even better. So we're going to now load our images. So first we're going to define an image size. And so if a GPU is available, if CUDA is available, then we're going to set the desired size of the output image to 512, otherwise 128. So we're just using a smaller size if there's no GPU. But it'll still be the same conceptually, and as far as the output, we get something the same. It's just different resolution. And then, so we define our loader variable here, and we're going to grab our transforms here. So we imported torchvision.transforms, and just in very standard way, we're going to compose our transformations. So we're going to resize our image. Remember, we need to standardize the input into our network. So we're going to resize it to be this size, and then we're going to transform it to be a PyTorch tensor here. So transforms to tensor. So that's our loader variable here. And now we're going to define an image loader function that takes in a path to an image, which is in an images folder in the local directory here. So it's going to use image.open, and here image we're importing from PIL. So we open our image, and then we pass into our transformation. So we transform our image here. We pass our image, and then we unsqueeze a dimension, a first dimension. So at the index 0 of our tensor, we're going to unsqueeze, create a new dimension here of size 1. And the reason is because our network is expecting a tensor with a shape of batch size, color channel, height, and width. So currently we only have color channel, height, and width. So we're unsqueezing a first dimension, so at index 0 of size 1 that represents our batch size. And here it's only a batch size of 1 because we only have one image. So once we have that, we have the proper dimensions, and now here from our function, we're going to return our image tensor here to device. So depending on what our device is, we're going to move it over there, and then the type. So make sure it's a torch.float. And now here we create our images, our style image and our content image. So for style, we're going to grab a Picasso image, and then for our content, we're gonna grab a person dancing here. You'll see in a moment. So we just assert here, make sure they're the same size, because they have to be the same size. Again, standardized input into our network. So now we're going to create a function that displays our images. So here you can just see it real quick. That's what our function is going to output. So this is our style image, Picasso painting, and then this is our content image. So that's when we input an image into our network, then again it's going to try to minimize the style between the input and the style image and the content, and it's going to output that new transformed image, so to speak, with a style transferred. So here we define here our a variable basically that reconverts into a pill image, because you cannot actually just display with matplotlib directly a PyTorch tensor. We need to have a pill image in this case. So Torch Vision Transforms has this nice method here, to pill function to pill image. And so we're just going to pass in our image there. It's going to on transform it. So it's nice. So we just had our interactive mode on. We define our image, our imshow function that takes in our tensor, and an optional parameter here as a title. So we grab our tensor to CPU, and then we clone it. So we're creating a copy here of our image, and then we squeeze it at 0. So we did the unsqueeze before to add a dimension. Now the squeeze at 0 is the opposite. So it removes that quote unquote fake batch dimension. So that just a batch size of 1, because again we don't need it in this case. We just need our standard image shape essentially, which is just the color, channels, height and width, no batch size dimension. Okay, so we have that. And then we pass in here our image here to this function. So it's going to convert it to pill image. And now we just show it. And if there's a title, we want to put a title on that. And here we define our plt.figure for each one, and just call our function. And we pass in the particular title here. And as you can see, our images are displayed. So very cool. So that's what we have. And now we want to define our loss functions. So again, we're going to have actually a style loss, and we're going to have a content loss. And they're going to be implemented in a similar way. They're different, but they're still they're similar how it works. So the content loss is a function that is going to represent a weighted version of the content distance of an individual layer. So we're going to have, for our input image, we're going to, after it goes through a convolutional layer, we're going to have a feature map, a set of feature maps as an output. That's a tensor. And then we are going to, here our content loss is going to, we're going to get a weighted content distance. So we have a mean squared error basically for our loss. That's how we define it. So that's how we calculate the distance between the content of our input and the content of our content image. So that's how we're defining how different they are, and we're going to minimize that difference essentially. And we have our weight. It's a weighted version of that distance. And again, feel free to pause here and make sure that this makes sense, and maybe do it at your own pace. But that's the concept of how it's working. And then this this content loss is going to be implemented as a module, as a nn.module derived class, and it's going to be put directly after our convolution layers. And this makes sense because again, we want to grab the feature maps output of our convolution layer for both our input image and our content image, and calculate that difference right there. So so that's how we're going to define it. So we define a class for our content loss, inherits from nn.module, and then we define an init function, a constructor here that takes in our content image, stores it here in a self.target. We detach it from the graph. And then we have a forward method here. So when we're doing the forward pass through the network, once we construct the whole network, once it goes through this layer, we want to calculate the loss. So we have our self.target here, our content that we stored, and then we're going to calculate the mean squared error loss here from between our input image and the content image, and we store that as our loss. And where's this f coming from? We imported that package here, torch nn.functional. That's how we have those loss functions there. Now the next is we define a style loss, and it's similar. Like we're still measuring a difference between those two. Like before, the output feature maps. But in this case, we want to actually calculate a gram matrix. And the gram matrix is the result of multiplying a given matrix by its transpose matrix. So we're going to define a function here, gram matrix, and it's going to take in our input image here. So this is what we're going to do. We're going to, so whatever image that we're putting into our into the matrix. So we're going to grab the size here, and it has four dimensions. It's a tensor of rank 4, and we're going to reshape it into a tensor of rank 2, or in other words, a matrix. And now we're going to do a matrix multiplication, so torch.mm matrix multiplication of our features here that we created, so our matrix, and then the transpose of that matrix, and then we're going to return it, and we're going to return it normalized by dividing by the number of elements in each of the feature maps. So once we have that, then we can now define our class for our style loss, which is going to be, again, another layer inheriting from nn.module. We'll see in a moment how we're going to construct this. And again, it's going to go right after our convolution layers, grabbing our feature maps and comparing them. But first here, we're going to compute our gram matrix for our style image. Again, detach it from the graph and store it as self.target. And once we do a forward pass through our network, here we want to calculate the difference. So we also compute the gram matrix for our input image here. And so once we have the gram matrix for both the input image and the style image, then we can now calculate the loss, so the difference, the distance between both of those two. And again, we want to minimize the loss. So we're minimizing, again, the style loss, and we're minimizing the content loss. And that's how our input image will be, quote unquote, transformed. So the next thing is now we're going to import our model. So we're going to import a pre-trained neural network. And we will use a 19-layer VGG network like the one used in the paper for neural style transfer. And so here we define our variable, here our CNN, and we grab models.vgg19. We pass in pre-train equals true as a parameter, grab the features, and then we move it to a device and then put it in evaluation mode, because we're not going to train this. We're going to put it in evaluation mode. So now VGG networks are trained on images with each channel normalized by a mean and a standard deviation. And now, so we want to create another layer, a normalization, an initial layer that is going to, again, help us standardize, normalize our images, make sure that the inputs to our network are all consistent and matching into what we expect. So we have our mean, which is a torch tensor. Again, we move it to our particular device, whether we're on GPU or CPU. And we define our class here. And our class takes in both of those tensors. And then here's just going to reshape it just to make sure that the shape is compatible and can directly work with our image tensor, which again has a shape of batch, size, color channels, height, and width. So we have that. We store them here in our self.mean, self.standard deviation. And now in our forward pass, our input image, we're going to subtract the mean and divide by the standard deviation. So there's just a standard normalization step here. Now the next step here, now we want to define a function here that is going to take in our CNN, our normalization, mean, normalization, standard deviation, style image, content image, and now our default layer. So here we're defining how many and which layers we want for our content and our style. So you can play around with this, but in this case we chose this. So we're gonna have five for after our convolution for the style, and just one for the content after the fourth. So that's what we have. So this function we're just creating a copy here, a deep copy of our CNN, and now we're going to create a normalization here module. So we just create an instance of our normalization here module, our normalization layer, and as we said, we pass in here our tensors and move into the device. This we just define this, and you'll see why we need it, just to have an iterable access to our list of content style losses. And now we're going to define our model, create our model, and it's going to be a sequential model. That's what we're working with here. And now to initialize it, we're just going to pass in our normalization layer, which is the first layer, right? When the images come in, we want to transform them and normalize them before we do anything else. So that's how we start our model. Now, for each layer in our CNN.children, so for each of those layers, we want to start adding layers, start constructing our model, our sequential model. So after that normalization, we want to start adding a convolution layer. Then And by the way, we're actually going to add, right after the convolution layers, so we're going to add our style loss layers and our content loss layers. And after that, we want a ReLU, pretty standard ReLU, transform of the output, and then max pooling layer, and then a batch normalization layer. So this is pretty standard convolutional neural network architecture here, but now we're just adding these quote unquote loss functions for the style and content after the convolutional layers, because what we're trying to accomplish here is neural style transfer. So again, feel free to pause, think on your own time, make sure this makes sense. But again, this is just pretty standard, just making sure if it's an instance, and if it is, we're going to store our name. And now, so for our model, we're going to add a module. So we're going to call this function add module, pass in the name. It's a sequential model, and then the particular layer here from our VGG 19 pre-trained network. So we're going to pass in that layer. So that's how we're going to iteratively construct our model here for our purposes. And now if the name is in the content layers here that we define, then we're going to do a forward pass here through the model, detach, and then we store it, and then we create our content loss, and then we're going to add the content loss here module to our model. So that's what we're going to add. So we're going to add, as we said, the convolution, ReLU, max pool, batch norm, but also in between conv and ReLU, we want to add these the content layers and the style layers. So, and here we're just printing the length of the model just to see kind of before and after, because in this case, we actually want to trim off the layers after the last content and style losses. So we're not gonna have all like 90, have a lot of layers here, content and style layers. So we're like past conv5, past the 5th layer, that's where we're going to stop based on how we define. So we don't need all of the layers coming right after that. That's because as we added those. So we don't need those. So we're just going to trim those, and that's why we actually have our I here, our variable here. So we're going to take just the layers that we need. So our function is going to return our model that we just created and our style losses and our content losses, because we actually want to print them later. Now here we're going to select our input image, create a copy, and so you can use white noise instead of our image, but here we're going to use our input image as our image, our content image as our input image, and this is the image that we're going to transform and apply neural style transfer to. So now the next step, once we have that in place, our model, now we need to define how we do gradient descent, and here is going to be a little different. So we're going to use from the Optim module here, we're going to grab the LBFGS algorithm to run our gradient descent. And unlike training a network, we want to train the input image itself in order to minimize the content and style losses. So we're going to train this image. So basically, the parameters for normally, and as we've seen before, our optimization, our gradient descent optimizer function takes in our model parameters and a learning rate, for example. But here it's going to take in as a parameter the actual input image, and it requires a gradient here. So this is what we're going to do. We're going to train the actual input image to minimize the content and style losses. So that's what we have. We define our get input optimizer and pass in our image, and it's going to return our optimizer, our gradient descent optimizer. Now then, finally, we want to define a function that performs the neural style transfer. And now, so we're going to iterate based on the number of steps, and you can change this hyperparameter, but here we just define it to be 500. And now, so we're going to run the backward methods on each of the loss modules to dynamically compute the gradients. And now the optimizer here requires a closure function that we're going to pass in. So when we're doing the gradient descent step, we're going to pass in an actual function here that reevaluates the module and returns the loss. Now, and we'll see in a moment just more detail, but here we have one final constraint to address, and The network may try to optimize the input with values that exceed the 0 to 1 tensor range for the image. And so we can address this by correcting the input values to be between 0 and 1 each time the network is run. So here we create our model. Here we have our function that we define that returns a model, style, and content losses, and our gradient descent optimizer here that takes in our image. So we have our model, our optimizer, and now we want to loop through the number of steps here. And we define our run variable here, and we're going to be incrementing it. So once we hit the number of steps, we can stop. So this, we're just going to loop through the number of steps. This hyperparameter that we chose. So again, just make sure that each time we come in and define our function and we update our function, the input values are between 0 and 1 for our image. So we zero the gradients, pretty standard, do a forward pass through our model that we created, and zero out the style score and content score and here that we're going to be printing out. And then for the style loss and style losses, we also want to append the loss here to keep track. We want to make sure that the style and content losses are going down, or we're going to be printing that. And then we multiply by the style weight and the content weight here that we define in our function, multiply a sign, and that's how we define our loss variable here. And now we're just because remember, it's a weight. It's not just the content, just the output of those layers, but it's a weighted for how we define the style loss and content loss. It's a weighted version of that distance between the feature maps in each case, the difference between those images, the input and the style, and the input and the content. So we have our loss there, weighted. And then we just do back prop here. So we do loss.backward, again, pretty standard how we do it. And every 50 steps here, we want to print out our stats here, see how we're doing, make sure that the output is what we expect, that the losses are going down. So we're just going to return our style score plus our content score. So we're going to return that total here from this closure function. And again, we just do our optimizer.steps, our gradient descent step, and we're going to just loop through 500 times and minimize the loss. And finally, we want to return our input image. So our input image is going to be changed. It's going to be changed, keep being changed, just basically transformed and iterated on to minimize the style and content loss. And you'll see it's very nice what we actually get. So we do our last correction here, make sure that it's between 0 and 1, the values here of our input image. And now we're going to run the algorithm. So this function that we just defined, we're going to call it here and return the output. And we're going to display the output with matplotlib, that output image. So again, just the CNN here, just the parameters that we defined, our pre-trained CNN, our normalization mean, our normalization standard deviation, those tensors, the content image, style image, and the input image. Again, these are overall the things that we need, those 3 images. So create a PLT figure, and then our function that we defined earlier to show it, and this is our output image. Turn off interactive mode, and finally just show. As you see here, we're printing out. This is just before trimming and after trimming the model. So this is just what we need, those 18 layers. So we're going to be optimizing, and every 50 steps, we're going to be printing out the stats. And as you can see, the style loss and content loss start at these values. And as we loop through this function, and we do our gradient descent backpropagation, we update here our weights, the losses are getting smaller and smaller and smaller. And finally, look at that. That's so beautiful. This is our output image. So we started here with these images. So the Picasso painting style and our content image here, and our output has now basically put them together. It's transferred the style of the Picasso painting into our image. So now we have this version. So very beautiful. So that's how you do neural style transfer with PyTorch. Thank you for watching. If you have any questions, thoughts, comment below, and I will see you next time.